Welcome to our countdown of the top 5 math problems that will blow your mind. You know, when most people think about math, they think about multiplication tables and maybe some geometry, but math, real math, goes way deeper than that. We're talking about the fundamental language of the universe kind of deep. Get ready to challenge your brain and see if you can solve these incredible puzzles. These are some of the biggest unsolved mysteries that mathematicians and computer scientists have been grappling with for decades, some for centuries. Let's dive in. First up is the Riemann hypothesis. And let me tell you, this one is a big deal in the world of number theory. It's all about prime numbers, those building block numbers that are only divisible by 1 in themselves. See, what Riemann wanted to know was if there's a pattern to how prime numbers are distributed across the number line. He came up with this complex formula, the Riemann zeta function, and it hints that there might be an underlying order to these seemingly random numbers. Now, if we could prove this hypothesis, it would be huge. It would have ripple effects throughout mathematics and even impact things like cryptography. The thing is, it's a tough nut to crack, and mathematicians have been working on it for over a century with no solution in sight. But that's the beauty of it, right? Just like exploring the vastness of space, some of the biggest questions in math remain unanswered. We're talking about pushing the boundaries of human knowledge here, people. The Riemann hypothesis is a prime example of how math can be both elegant and incredibly complex at the same time. It's a puzzle that forces us to confront the very nature of numbers and the fundamental forces that govern our universe. And trust me, the implications of solving this thing are huge. It's not just about some abstract mathematical concept, it has real-world applications in fields like cryptography, which we use every day to secure our online communications. So yeah, the Riemann hypothesis is a big deal. And who knows, maybe one of you watching this will be the one to finally crack the code. Next up is the P versus NP problem, and this one is all about the limits of computation. Imagine you have a really hard problem to solve, like finding the best route to visit a bunch of cities, and it takes your computer ages to crunch through all the possibilities. Now imagine there's a magical shortcut, a way to verify the solution quickly, even if finding it in the first place is super tough. That's the heart of P versus NP. P problems are those we can solve relatively easily, while NP problems are those where verifying the answer is easy, but finding it might take practically forever. The million-dollar question is, are P and NP actually the same thing in disguise? Could there be a clever trick, an algorithm we haven't discovered yet that could crack NP problems wide open? If P equals NP, it would revolutionize everything from drug discovery to artificial intelligence. But if P is not equal to NP, well, that means some problems might just be fundamentally hard, and that has profound implications for our understanding of the limits of computation. Now let's talk about elliptic curves, those beautiful curvy shapes that you get from equations with variables raised to the third power. The Birch and Swinnerton-Dyer conjecture dives deep into the world of these curves and their rational solutions, those elegant points on the curve that can be expressed as fractions. What this conjecture tries to do is connect the arithmetic of elliptic curves to something called their L function, which is a sort of mathematical fingerprint that encodes information about the curve's behavior. Think of it like this. You have this intricate, beautiful curve and you want to understand its deepest secrets. The L function is like a secret code, and the Birch and Swinnerton-Dyer conjecture provides the key to crack that code. What makes it so fascinating is that it connects seemingly disparate areas of mathematics, bridging the gap between geometry, algebra, and number theory. It's like finding a hidden passageway between different rooms in a vast mathematical mansion. And just like the other problems we've talked about, proving this conjecture would have huge implications for our understanding of numbers and their relationships. It's a testament to the interconnectedness of mathematics and the power of human curiosity. Shifting gears now, let's dive into the fascinating world of fluid dynamics with the Navier Stokes existence and smoothness problem. This one is all about understanding how fluids move, from the air we breathe to the water flowing in our oceans. The Navier Stokes equations are like the fundamental laws of fluid motion, but here's the catch. We don't even know if these equations always have smooth, well-behaved solutions. Think about it. We use these equations to model everything from weather patterns to airplane designs, but we're still not sure if they always make sense. The challenge is to prove that in 3 dimensions, these equations will always have solutions that are physically realistic and don't go haywire with crazy, unpredictable behavior. Solving this problem would be a major breakthrough in our understanding of fluid dynamics and have enormous practical applications. Imagine being able to make accurate long-term weather predictions or design even more efficient airplanes. It's a problem that highlights the challenges of grappling with the complexities of the physical world and the power of mathematical tools to help us make sense of it all. Last but not least, let's journey into the abstract realm of algebraic geometry with the Hodge conjecture. This one is a real head-scratcher, dealing with the geometry of complex shapes in higher dimensions, things we can't even visualize. Imagine trying to understand the shape of a shadow in a world with more than 3 dimensions. That's the kind of territory we're talking about here. The Hodge conjecture proposes a way to study these complex shapes by breaking them down into simpler geometric building blocks, kind of like using Lego bricks to construct a complex structure. It suggests that certain geometric features of these shapes can be represented by equations involving only whole numbers, which is a surprisingly elegant idea given the complexity of the objects involved. Proving the Hodge conjecture would be a major triumph for algebraic geometry and open up new avenues for understanding the structure of the universe at its most fundamental level. It's a testament to the power of abstraction and the beauty of mathematical thinking. Thanks for joining us on this mathematical journey. We've explored just a tiny fraction of the mind-blowing mysteries that mathematics throws our way. And it's this sense of endless exploration that keeps mathematicians and scientists like me always coming back for more. Don't forget to like, subscribe, and hit the bell icon for more mind-bending content. And let us know in the comments which math problem you found the most fascinating. Was it the elegance of the Riemann hypothesis, the computational puzzle of P versus NP, the intricate curves of Birch and Swinnerton-Dyer, the fluid dynamics of Navier Stokes, or the high-dimensional geometry of Hodge? Until next time, keep those math brains buzzing.